Good evening, ladies and gentlemen. My name is Markus Pfeifer. I work for today's sponsor, and that apparently qualifies me to bore you over the next couple of hours with what I call the art of approximation. And does it work? Okay. And, this is my agenda. First, I'll talk about approximation theorems. Then I'll talk about my favorite model class, hidden Markov models. And then I'll talk about what you can do with them. Filtering, smoothing, the algorithm for that, the forward-backward algorithm, and another algorithm, the beta-B algorithm. And then I'll justify the word art. Don't say it's do. So, yeah. A major justification for what data scientists are doing are approximation theorems. And two approximation theorems that are often cited are the sigmoid approximation theorem and the universal approximation theorem. The sigmoid approximation theorem basically says, take high-dimensional data, so it's just some numbers, and each of these numbers you can multiply through a fixed number. So you have different numbers that you multiply them to, but for each one it's fixed. Then you have to add them up. You may add another number, and then you put them through a sigmoid function. That is a function that starts at 0, smoothly goes to 1, and then stays there. And the theorem says that these functions and all the possible linear combinations of these are enough to approximate any continuous function on a compact set. So that's something, but only 2 years later it was shown that actually you don't need to take sigmoid function. Any arbitrary function that is continuous and bounded, but not constant, is enough for that. Now,
even linear?
Are they bounded?
No.
Okay, so, okay, on a compact set, yes. Okay, now, thanks. So, are there older theorems like that? I mean, it sounds like we could now just go ahead and go approximate anything. But how old are theorems like that? And it turns out that they actually date back to the 19th century. There was a theorem proven by Weierstrass that says you can approximate anything with polynomials. And even earlier, some guy called Fourier did the same thing with sine curves and cosine curves. And we know he was successful because we still use Fourier series. So, what progress has been made between 19th century and now? More or less now. I would say not that much actually. Just approximating functions with functions that we can control is actually the easy part. I would even say it's almost trivial. The hard part is this. What we are given are not the functions that we want to represent, but data, the red dots here. And we try to look for good approximations. And here are two proposals, the blue curve and the purple curve. Which one is better? Well, here you have the same data, but this time not as dots, so you can easier follow what's happening. And we see that the purple curve, in a pointwise sense, is actually closer to the data. So maybe it's better? Well, maybe not. So the purple curve turns out to be a polynomial of degree 20 that was tailored so that it fits this red data. But we know polynomials are not great. They just run away like this. So maybe the blue curve is way better, and I actually know it's way better because the red data is just the blue curve plus some Gaussian noise. So, So, yeah. What we saw here is called overfitting. The good thing is we have a name for it. The bad thing is there's not much theory for that. So actually, what I just told you, you have some curve that fits the data well, but as soon as you add more data, the curve is not that good, and there's a better curve. That's the definition of overfitting. And with such a simple definition, there's not that much that you can do. So the best techniques that the geniuses over centuries have come up with to avoid overfitting is, well, okay, let's just divide the data in 90% and 10% and use 90% to learn the data and 10% to evaluate it. And okay, then you can detect that a curve like the purple curve is not great. And if you do this with lots and lots of splits of 90% and 10%, so you don't need to take just this split, you could also take this split, and any arbitrary split. You don't even need to take 90 and 10, you can take 80 and 20, whatever. So it is possible to find out, okay, with one split you have a good model, with another split you have a bad model, and you just take the best. So that's the best technique that we have come up with. It's called cross-validation. And there's no guarantee whatsoever that we will actually ever find this blue curve. And that's bad, in my opinion. So what any good data scientist should actually rely on, whenever it's possible, is models. So in this general scenario, there's just not that much you could do. So yeah, better look at models. And the model class that I looked at is hidden Markov models. For one simple reason, they are quite general. They can approximate lots of things, but at the same time, they're specific enough to so you actually can do some theory on them. Hidden Markov models are known since the 1960s, and they have a lot of successful applications like speech recognition. Actually, the earliest algorithms in that field were hidden Markov models. NASA used them in order to track their spacecrafts. And in the 90s, there actually was an application for finding coding regions in the genome. So in the genome, there are regions that actually encode something, and other regions that don't, at least as far as we know. And hidden Markov models can actually represent that. Maybe these are a bit oversimplifying models, but they actually work well enough that they are still around. And a good thing about hidden Markov models is they are rigorous. But what are hidden Markov models? Well, say you have a colleague that only has two moods, good and bad. And now from observations, you know that there's a small chance P that after a good day, he has a bad day, and there's a small chance Q that after a bad day, he has a good day. And obviously the chance that the mood will remain the same is 1 minus P or 1 minus Q, respectively. Now you do some further observations, like how many coffees does our friend drink on a good day or on a bad day? And you will end up with something like this. So say on a good day, there's a 50% chance that our friend will drink one coffee, a 30% chance that he'll drink 2 coffees, while on a bad day, he drinks significantly more coffee. So there's a 40% chance that he'll drink 3 coffees, and even a 10% chance that he'll drink 5 coffees, which he would never do on a good day. And provided that your measurements don't somehow affect the outcome of the process, you will end up with something like this. So here you have the moods, and they always depend on the last day. So you encode causality. And now you encode some other causality here. You encode the number of coffees depend on the mood. And let me. So, obviously, you don't need to reason about some colleague with coffee and moods. So you can actually do this with formulas, and it looks like this. Don't worry, I won't go too much into details. Now, what we're actually interested in is, of course, not the model itself. We are interested in inference, and in this special case, we look for, okay, we know our friend drank this or that amount of coffee. What was his mood? So, as a formula, we are interested in this. Just to explain a little bit of the indices here, we are looking for some phi nu. Nu means our prior knowledge, the initial mood distribution, so to say. That's why it's called nu, that's what we knew. From day k through L, so what went on in between k and L, given n, where n is just, with all observations from 0 to n. And this formula as a whole just means it should be a conditional distribution. Now, what you can immediately read off from this is if it exists, it's unique in LP sense. What you can't read off is, does it exist? Yes, mathematicians actually ask such silly questions, and we can answer it by simply computing it. So here we see a computation of phi from day 0 to day n plus p, given all the observations from 0 to p, so 0 to n, so we go p steps into the future. And the formula here basically means we can concentrate on computing this here, so everything in between day 0 and day n, and then we just apply our model equation. So how do we compute that one? So everything from day 0 to day n, well, it's that formula, and all I want to say about this is it looks a bit like the Bayesian equation, the Bayesian formula. So here's actually a likelihood, and this is, it resembles a prior. So you don't actually apply just Bayesian theorem, you actually have to show that in this recursive setup it actually some formula that resembles the Bayesian theorem actually applies. Now at this point we are actually more or less done, because now we know that all the individual days have a distribution. So if we are interested in some day k in the middle, all we need to do now is integrating out everything we don't care about. Now, integrating out everything we don't care about, that sounds like a crazy idea, because actually what we have to integrate over is a path space. We integrate over not only good mood, bad mood, but over all possible combinations of them from day 0 to day n. And with every new day, the number of paths doubles. So that's a bad idea. Illustration that it's a bad idea. Another illustration that it's a bad idea. So obviously I wouldn't stand here if this was all we could do. Let's actually use some common sense. So say we are only interested in the next day after our observation sequence. That's called prediction. And obviously, well, it's just one distribution. Maybe we can build on that. So, say now we want to condition on a new observation. That's called filtering, and that actually is the Bayesian theorem. So that's pretty easy. And again, we have just one distribution here. Now the tricky part: how do we get backwards in time? Well, what we can do is we can condition that guy on this distribution. We end up with a conditional distribution here, and then we can just marginalize that one out. And what we have achieved now is we actually have conditioned that distribution on that new observation, and we are in a situation that actually looks pretty much the same as before. So we can just recursively apply that. That's called smoothing, and so we can actually tell the distribution of mood at any arbitrary day. And in case you're interested, that's the formula for that. Now, what we did was we reduced a very big problem just by using the structure of our model. By the way, that's called the forward-backward algorithm. Also the alpha-beta algorithm, because of these variables. In the finite scenario, these are just vectors. And in this more infinite scenario, alpha is a distribution and beta is a function. But what I wanted to say is, yeah, in a way we just apply the Fabini theorem from math, and we use that our model is structured in a way that we can write out some terms. That's it. And in the same way, we can actually answer a different question. Again, a question that would, in a normal way, in a normal scenario, require to know the entire path space, but here not. And that is finding the optimal path. So we have a lot of observations, and we want to know the optimal, so the most likely distribution, the most likely path of moods. And here's how we do this. We actually just go forward in time, and then at some arbitrary point where we say, okay, now we want to know everything in the past, we say, okay, we're done. And at the end of this process, we can just take the most likely distribution at this endpoint. But now, how do we get back? We can't just take the best point here, right? Because let's go back to the coffee example. Say here you're pretty sure that your friend has a good day, but here he drinks 5 coffees, so probably a bad day. And say the probability after a good day that he has a bad day is pretty small, then maybe saying that here he already had a bad day is a better guess. So we have to factor in these transition probabilities, but then we are again in a situation where we can just do this recursively, and we can go arbitrarily far back into the past as long as we have observations. And in case we're interested, these are the formulas. So everything I said so far is actually pretty well known. Let's do one thing now that is not that well known. Say the number of observations is very large, then, well, the BTB algorithm requires that you have the entire observation sequence, right? As I just told you, you have to take into account the transition probabilities. Now, if you want to know the optimal path in genome, coding regions, no coding region, then that would take a while. So what we can do instead, well, we can't do this, we can just take the maximum at the end of the, at an arbitrary point of the observation sequence, but we can do this step back in time, this taking into account the transition probability with any possible point here. And it may happen that two or more of them have a common ancestor in that diagram. And if that happens often enough, we may end up with a single point. And then we know the entire past. So this is a simple idea I could have come up with, you could have come up with, if you knew the model a little bit. But it actually only was discovered in 2007. So pretty recent. It shows that it's still an ongoing topic in research. Yeah, here are some things that are still open. What we don't know is what are conditions on a hidden Markov model so that can actually happen. Because you can easily come up with hidden Markov models where this can never happen. We have some necessary and sufficient conditions for that, but I would argue they are not really satisfying. So that's one problem. Another problem is what actually is the expected time for that to happen? How long do you have to wait until the next part of this global Viterbi path is revealed? We don't know. So if you have too much time and need some mathematical problem, here is one. So, to come to the end slowly, why are hidden Markov models cool? Well, first of all, they can be infinite. If we take away the Viterbi algorithm, anything I told you can be done in an infinite case. And one example is the Gaussian linear state space model. And filtering is just the Kalman filter. Maybe some of you know that. And smoothing is the Rauchthun-Striebel smoother. So in case you wonder where the names came from, that's where. In the finite case, it's actually known that hidden Markov models can approximate all ergodic processes. What is an ergodic process? Well, it's just a little bit more than a stationary process. Stationary process is, it always looks the same. It doesn't mean that it's identically independently distributed. So if you condition one point in time on some other point in time, there may be dependencies. But in a prior sense, if you look at some arbitrary point in time, it looks the same always. An ergodic process is just as you collect observations, you actually come closer and closer to this stationary distribution. So there's no one at the beginning of the universe that throws a dice and then everything is predetermined. Yeah. So in a way, ergodic processes encompass everything that science really cares about. But that's actually already a challenge, because in the real world, there are processes that are not ergodic. Second law of thermodynamics says tomorrow is warmer than today. And in the infinite scenario, it's actually worse. We know that optimal filters only exist for a very narrow model class. There's a reason why I brought up linear Gaussian models, because that's one of the classes where it's known that it works pretty well. Everything else, extended Kalman filter, unscented Kalman filter, and so on and so forth, it's not optimal. We can't say in advance that they will work. As soon as we deal with non-linearities, for example, the only thing that could guide us is experience. And that brings me back to the beginning of the talk. I would argue that means it's an art. We don't yet have a theory when something will work and when it won't work. There's no guiding principle how to engineer good models. Yeah, only experience. And that doesn't mean that it's useless, because before Newton there were good engineers and good astronomers. Before the theory of evolution you already had good biologists, and before the periodic table of elements you already had good, okay, back then there were probably alchemists, but okay. And just to show you some use cases of hidden Markov models. I don't talk about other models, just hidden Markov models. They can be used, for example, for speech tagging. So if you try to attach meaning to individual parts of sentences, it can be done with it. Robot localization. If you have some industrial robot and it wants to find itself in a factory, hidden Markov models. Navigation. There's a good chance that you will find a Kalman filter in your car if you have a Navi. Genetics and speech recognition, these are some topics that I already mentioned. And here's maybe a future use case. I just said, okay, we don't have a theory, but we have experience. And in my experience would suggest that maybe we could have a hidden Markov model traffic control system. Like you want to coordinate what different traffic lights are doing. Pretty reasonable. And yeah, we are looking forward for you to partner with us to make these things happen. Thanks for your attention.
Markus, we typically do a small round of questions at the end, and just a show of hands. Who understood all of that? Not alone. I put my hands down before. But then, if you do need a math, I forgot to say, you actually studied IT and mathematics, so that's maybe why you have this deep background. At the end of the day, AI, it's what someone called once statistics or math on meth, statistics on crack. Yeah, so it's very much the fundamentals that we went into. And don't worry if you didn't understand all of it. I didn't either, but some of the things I did understand and they really made sense. So
probably the coffee example.
That's good, but yeah.
Yeah, thank you very much. I also like how you managed to translate these complicated formulas in these simple sketches, and also in the direction of understanding it a little bit more in these use cases that you showed. Could you say a little bit more where exactly the hidden Markov model would be used in one of these use cases? I don't know, big traffic control system. Where's the hidden Markov model there, and what kind of benefit does it then have in this use case?
Well, okay, to get to this traffic control system, well, you somehow need to predict what the traffic situation will be, given some data, like you have cameras on some positions in the city, so you can guess what's going on right there, but then there are parts that are hidden, and you would like some time dependency. So my guess is that hidden Markov models could help there.
And then, if you compare it to a Kalman filter, because you said the Kalman filter is like a simple version of the general Markov models, right?
Mm-hmm. Well, I'm not sure yet how I would do this, but okay, you have finitely many points in your city. Feels more like a finitary problem, but yeah. As you said, Kalman filters are generalizations. In Markov models are a generalization of Kalman filters anyway. So yeah, both could be. Yeah.
If you apply this to finance, how many states will you model? In fact, trying to predict just 2 states, like in here, that's usually the easier case. Most investment professionals would like to have probably some more states, like 3 or 5. Have you some experience with this?
Yeah, I don't really know much about finance. I know that people do stochastic integrals there, but really.
So you always use just two states?
In Markov model, but any
not always.
Yeah.
But,
you can choose any finite amount.
Yeah, I know. Therefore, I was asking whether there's some experience with some.
Yeah, and so we are physicists here, and at CERN you use Kalman filters to do the particle tracking. And these are multi-dimensional states. You have all kinds of stuff like the momentum, which is three-dimensional vector, the position, which is a three-dimensional vector. So there you have also many variables that you propagate through time.
Concerning these natural language tasks like speech recognition and part of speech tagging, I mean, this is also an area. This fancy new neural networks have also been applied heavily. So how do you hit Markov's model compared to them? I mean, if they're still used, so they couldn't be that much worse than these fancier methods.
Well, I think they're both in use still. Honestly, I don't know which one does better. I mean, it's just one tool. It's a tool that I find interesting because there's some theory there, but obviously if you only know a hammer, everything looks like a nail.
Yeah, so thank you.
So the pizza is still not here. It's open to come. We will continue with the second speaker.
Danke.